All right, fantastic. Hello, everyone, and welcome to another edition of Beneath the Surface with the Marine Mammal Care Center. This is a lecture series brought to you by Marathon, proud support of Marathon, to bring you some really awesome lectures in the world of marine mammals and what I like to say is marine mammal adjacent content. We have a wonderful speaker for everyone tonight. We have Dr. Gwen Goodmanlowe, who's going to be talking to us a little bit about worldwide contaminants in marine mammals. Dr. Goodmanlowe is currently a lecturer at California State University at Long Beach. And in her previous ventures, she got her degree from Fairleigh Dickinson University. Decided New Jersey maybe wasn't where she wanted to spend her entire career, and found the great state of Hawaii to do some really awesome research on Hawaiian monk seals, I believe. And from there became her lecturer position at Cal State University, Long Beach, where she also, I believe, got her master's degree. So let's see, I'm gonna admit some more people. And she's gonna be talking to us about some really cool stuff that's happening locally, as well as I'm sure broadly. And I'm excited to hear what she has to say. So I'm gonna toss it over to you now, Dr. Goodmanlowe. Oh, and just for everybody who's watching right now, the lecture tonight is gonna be about 45 minutes to an hour. We're gonna hold our questions till the end of the lecture to ask. If you have any kind of logistical needs or anything like that, I'll be monitoring the chat. If you need anything, you can certainly ask me to support you there. So with that, Dr. Goodmanlowe, I'd like to pass it over to you.
Thank you, Dave. All right, let's see if I can do a screen share here. Oh, you have to unshare your screen first, Dave.
Thank you.
I know, technology, right? All right.
Right.
So let me do this. Oh, there's my cat. Sorry, that's not what we're talking about today. Let's see.
As long as none of us turn into a cat and start talking.
Right, there you go.
That'll be fine.
All right, let's see what we got here. Okay, so today I'm going to be talking about contaminants in marine mammals, and I'm going to start with a background of contaminants, what they do, the most common ones, things like that. And then I'm going to talk about what we see worldwide in marine mammals. And then I'm going to talk about some research that we've done off the Southern California coast. And then if we have time, I'll do a comparison to some a remote location called Palmyra Atoll. All right, so here we go. Let's see here. Get this to work. Okay, so let's start with what's going on in the world, right? So we know that there are a lot of people on Earth right now. I just looked this up today, and we have over 7.9 billion people on Earth. That's as of November 2021. Over 39 million people live in California alone. Over 10 million live in LA County, and plus 3 million in Orange County. So we have about 13 million people along our coast. And the fact of the matter is that over half of the world's population, if you look at these maps, actually lives along the coast. And there's a reason for that. It's because originally when we were, trying to transport goods, transporting them in the water along rivers and streams and the ocean was actually easier than transporting them along land. So that's where the cities ended up being built. Now, because so many people live along the coast or near the coast, water quality has decreased worldwide. A lot of people still to this day, even though it kind of blows my mind, think of the ocean as kind of a big trash dump because, in the past, if we threw stuff in the ocean, we thought we would never see it again because the ocean was so large. However, we now know that that's not really true, and we shouldn't be polluting the ocean. But as an example, I grew up on the East Coast, New Jersey, as Dave told you, and I used to go fishing with my father and my brother all the time when I was a kid. And even when I was a kid, and my dad would throw like soda cans and stuff overboard, I would say, "Dad, what are you doing? You're throwing trash in the ocean." And my dad would say, "Oh, the fish love it." Well, I'm not really sure that's true, but even way back when, before like pollution was an issue or we really thought about it, I was still concerned about it. This is a picture of a place called the Northwestern Hawaiian Islands, which you may have heard of before. And this is a pristine, supposedly pristine area. Sorry, I apologize for my dog howling. Um, oh my gosh, this is a pristine area that is closed to the public and only researchers can go there. They've even closed fishing. But if you look at this picture, you see lots and lots and lots of trash. So this is in the middle of a gyre where a lot of plastic pollution and glass pollution and other types of pollution land on these little atolls. And this is an area where endangered species nest and reproduce and are supposed to have, a good area to live. So this just shows you that even though, we may not see it, say in Long Beach where they have, machines that pick up the trash, there are areas like this that are supposedly pristine where you see lots and lots of pollution. Okay, so let's get down to the nitty gritty here. So I'm not talking about plastic pollution. I'm not talking about oil pollution today. That would take me probably 3 lectures. I'm really only focusing on contaminants. So I have to define contaminants for you. So the definition of a contaminant is a polluting or poisonous substance that makes something impure. That's the broad definition of it. So how do we get these though? How do they get into the ocean? Well, most contaminants enter the environment from industrial and commercial facilities. We have oil and chemical spills. We have non-point pollution sources like roads and parking lots, storm drains. So, the materials that we make roads from are actually pretty toxic. And every time it rains, a little bit of that leaches out, goes in the storm drains and can go into the ocean, or rivers and streams that then go into the ocean. We have wastewater treatment plants and sewage systems that sometimes overflow. And a lot of these things have been around for decades and are slowly but surely leaching into the ocean. And I'll talk a little bit more about where that is and that in a second. So, so we have oil and chemical spills, and we have those non-point sources like roads, parking lots, et cetera. Now, some of the examples of contaminants in the ocean include nitrogen, which you would think is more of a natural kind of pollutant because, we are defecating and, nitrogen is in our metabolism, metabolic waste. So that's kind of more of a natural pollutant, but it can still be considered a contaminant. Bleach, salts, pesticides, which I'm going to talk about, metals, bacterial toxins, human or animal drugs, which we don't really talk a lot about, but things like antibiotics and birth control hormones. Every time you put something like that into your body, you're not absorbing 100% of it, and some of it comes out when you pee. And that goes into the wastewater treatment plants, which are really treating for bacterial things, not really these kind of drug-related things, and that ends up in the ocean and causes issues for a lot of animals. And then we have plastics and oils and things like that. All right, so I am going to only focus on organochlorine contaminants in this talk because it's relatively short presentation. Okay. So what are organochlorine contaminants? So organochlorine contaminants are also known as chlorinated hydrocarbons, so you may know them either way. And they actually include a huge family of compounds, which include the most common ones that you might have heard of, which are DDT and PCBs. And I'll talk a little bit more about each of those in a second. So organochlorine contaminants are what we call lipophilic and hydrophobic. And those are 2 different things. So lipophilic means that they love fat, they're fat loving. So that means they bind to fat. But on the other part of that, the other flip side of that is not only do they bind to fat, but they are hydrophobic, which means they don't like water. So if they were lipophilic and not hydrophobic, you might be able to get rid of them a little bit easier, but because they don't like water and they do like fat, once they get in an animal's body or a human's body, they are kind of glommed onto the fat part, and it's very difficult to get rid of those. They're also chemically stable, which means that they persist in the environment for very, very long periods of time, and also in the body as well. Oceans actually act as sinks for organic chlorine compounds because it's just difficult to get rid of them. So once they get into the ocean, they're kind of there and they're available for being absorbed by a variety of organisms. And so basically for every animal and every marine mammal that they've ever tested everywhere in the ocean, they have found some levels of organochlorine contaminants. That's pretty scary because when you think about it, We don't produce or manufacture organochlorines or anything like that in the Arctic or the Antarctic, and yet marine mammals that have been studied in both of those very remote places have significant levels of organochlorine contaminants in their bodies. So you need to be a little bit scared about that. Okay, so let's talk about some of the most common ones. So number one, we're going to talk about are dioxins, which are also known as polychlorinated by dibenzodioxins, PCDDs. And they're an interesting contaminant because they are some of the most toxic chemicals known to science. There is almost nothing that is as toxic as dioxins, but we don't really talk about it that much. There's no safe level of dioxin, and even trace amounts are not actually considered safe. So how do we get dioxins? Well, they're actually formed from industrial processes that involve chlorine, like waste incineration, chemical and pesticide manufacturing, pulp and paper bleaching, and the incineration of PVC. So if you have a PVC pipe and you decide you're going to get rid of it and you burn it, you're putting dioxins into the atmosphere. Dioxins are also found in cigarette smoke, in all bleached products, because it has to do with the manufacturing of bleach, including tampons, which are bleached, but found in relatively small doses, thankfully. In addition to cancer, exposure to dioxins can cause severe reproductive and developmental problems. So how, as a human, do we actually get dioxins in our body? Well, if you look at this table, what you see is that the number one source of dioxins for humans is the ingestion of beef. So, you know, you've read about you should be like more vegetarian, you should cut down on beef, cut down on chicken, cut down on animal protein. This is a good reason why. Okay, beef is the number one source of dioxins in the body, and that's because it floats around in the atmosphere, it lands on the ground, lands on the grass, and cows ingest it. It's also found in dairy in pretty high levels, milk, chicken, pork, eggs. Inhalation is very low, and nobody really should be eating soil, but thankfully it's not really found in soil very high, and it's negligible in water, again, thankfully. Okay, so the most toxic form of dioxins is known as PCDD, and that became a well-known contaminant during the Agent Orange years because it was used as a defoliant in the Vietnam War. Most recently, dioxins have been in the news with some different crises. So there was the pork crisis in the 1980s. President Yushchenko of Ukraine was poisoned in 2004, and that's actually before and after picture. That's what he looked like before he was poisoned. That's what he looked like after he was poisoned with dioxins. One study found that a North American person eating a typical meat-based diet will receive 93% of their dioxin exposure from the ingestion of beef. So again, another reason why you might want to cut down on the beef. Marine mammals that have been tested for dioxin have shown the highest levels around in the Baltic Sea, and they found dioxins in the seal blubber about 15 times higher than what's typically found in human fat tissues. So they have a very high level of dioxins in their body for the ones that have been tested. All right, moving on to PBDEs, polybrominated diphenyl ethers, PBDEs. These are the anti-flammable contaminants that are used in things that you want to allow to get high heat but not burst into flames. So these are really ubiquitous. They're used in lots of different things, electronics, they're everywhere. Your TV, your cell phone, your car, your toaster, your sofa, things like that. So, you know, it used to be that you had 17 minutes to get out of a burning house because we had a lot of natural fibers like cottons and things like that. Now you only have 4 minutes to get out of a burning house because of all of the synthetic fibers that we have, you know, in our curtains and our bedding and everything like that. Because they do not want, you know, kids' clothes to burst into flames or pillows, they put PBDEs in children's clothing and pillows. So when you're sleeping at night, if you're not using a down pillow, there's a good chance that there's PBDEs in there, which is pretty scary. The pollution of PBDEs has been found in 20 different countries and really remote locations like the North Sea, the Baltic Sea, the Arctic Ocean, basically everywhere that scientists have looked. The tissues of whales, seals, birds, bird eggs, moose, reindeer, mussels, fish, all along the food chain, everywhere. Human breast milk, hair, fat, and blood, hot dogs and hamburgers have also, there's also levels of PBDEs in those things that you're eating. So we know that they are really dangerous and really bad. So there's been a move to limit or control the production, manufacture of some of the PBDEs. And in fact, in 2006, California enacted a law that prohibits the manufacture, distribution, and processing of some of the worst PBDEs. But this is a class of chemicals, so it's just the worst ones that they prohibited the manufacture of. But that doesn't mean that the United States has stopped manufacturing them as a whole. And also, we still allow the import of these things from various countries like China and other places that are making these kind of, these products that we don't want to burst into flames. So all of these things are still coming into the United States. They're still in the environment. It's pretty scary. This is a figure that shows you the levels of PBDEs in ring seals in human milk in Sweden, and the worldwide production of just one of the congeners of PBDEs. And you can see that it's on the rise. Again, the more and more synthetic products, that we use in our homes and our clothes, we have to do something so that they don't burst into flames. And so the production and use of these PBDEs has increased quite dramatically. Okay, here's a figure that shows you PBDE data. The colored dots are from 2004 to 2007, and it just shows you that along every coast there's relatively high levels of PBDEs. And this was looking at the transport of PBDEs and actually trying to gauge the levels of them in the blood. So this is what the study that they did was about that. The reason why they were looking at that is because PBDEs may block the transport of thyroid hormones throughout the body. And so it's not just like cancer causing and things like that, but it actually disrupts hormone regulation in humans. Okay, and they've also found it in orca in the Pacific Northwest. All right, now we'll get to the two that we know the best, DDT and PCBs. So we'll start with DDT. DDT, when we talk about DDT, we're actually talking about a whole class of congeners of this chemical. So that's why we call it small t DDT. So this is total DDT, diphenyl trichloroethane. It was first developed in Germany in 1874, but they didn't really actually use it for much. They discovered it, they made it, and then they kind of let it go. And then in 1939, they realized that they could use it as an insecticide. So then they really started producing it in high quantities then. So they used it to control malaria, typhus, and other insect-borne diseases. And they used to just, blow it out, in the public. There's people just standing right there, right in front of the DDT spray. They dusted World War II soldiers with it to control lice. They sprayed it on crops and forests to control insects. They used to spray it inside airplane cabins. And I'll tell you that as a kid, I grew up on the Jersey Shore in the summers, and I can remember when they used to spray DDT for mosquitoes, and my mom would hear the prop planes coming, and she'd say, "Everybody inside and close all the windows," even though it was hot in the summer. And I can remember then after that going outside and playing with the little pellets that I now know were DDT outside. So yeah, we still did it in my lifetime here. Okay, so they stopped producing and using DDT in the United States in 1972 when they realized that, when Rachel Carson wrote Silent Spring and realized how bad it was. But they still use it for disease vector control in other areas, just not the United States. And in fact, this is an advertisement for 1947 for the Department of Agriculture, and you can see that people were, they promoted people to, housewives really back then, to spray this inside their homes to control like flies and any kind of bugs and things like that. Now, the good news for DDT is that you have to ingest it for it to affect you. It's not absorbed through the skin, which is, one good thing as far as how we sprayed it around our environment. Okay, so as I said, production and use continued until 1972 when it was banned in most places except for disease vector control. Here's a plant that's still producing it. And the thing that you have to remember about DDT is that it is the most effective way to control malaria. So in poorer countries where we can't afford to, like do other things like give everyone a pyrethrin netting over their bed or something like that, really the easiest, cheapest way to control malaria is actually to spray this in the environment. So this is a great figure. I love this figure because it really is so clear. So this is, it shows you DDT house spray rate, and that's in the black squares and the line, and then the cumulative malaria cases. And you can see that when we stopped using DDT, the number of cases of malaria started increasing dramatically. So it is the most effective way to control malaria. And so it is still used in certain places like Africa and India and places like that. Okay, but we know that it is very harmful to wildlife. So here's a picture. Rachel Carson wrote Silent Spring, and she was, trying to alert people to fish and things like that. And nobody really listened to her until she wrote that book. And then she got the attention of the general public. So the effects of DDT was first noticed during the 1960s in fish, but then it started showing up in birds. So, and you probably already know this, but the way that this affects birds is that it doesn't kill them. It does not kill them outright. So if it killed them outright, I think people would be more aware of what's going on. Like when you see a pollutant like plastic, where a whale washes up and it's got plastic in its stomach. But basically, the adults still live. The problem with DDT is that it interferes with calcium deposition. So the birds mate and they produce an egg, and then the pelican will sit on the egg to incubate it. And because the DDT interferes with calcium deposition, the egg is so weak that the mother that's sitting on the mom bird that's sitting on the eggs will actually crush the eggs, and therefore the babies can't hatch. They can't ever develop. So here we see Caspian tern eggs. You can see they're really soft. Here's some pelican eggs that were collected from Anacapa Island in the 1960s. And you can see here's normal eggs, and then here are DDT affected eggs. We do know that all people in industrialized nations have some levels of DDT in their tissues. So everybody has it in there. There's basically no getting around that. All right, so what are some of the detrimental effects of DDT, and then the metabolite, which is called DDE? So that's after you've metabolized the DDT. So in humans, we know we have evidence that it causes developmental abnormalities in young. It causes reproductive diseases, neurologic diseases. We have a correlation of DDT and cancer that's been relatively recent. Breast cancer and DDT was just discovered about 10 or 15 years ago. Testicular cancer and DDT has been very, very recent, the link between those two. A also really recent effect is childhood diabetes and obesity. So they're linking that to DDT in the body as well. And there's also liver and nervous system damage. So it's nothing to be reckoned with. In sea lions, that's what they've studied it mainly in, because there's so many sea lions along our coast. And so you can really kind of do correlation studies. It is very difficult to measure a cause and effect, and I'll talk about that in a second. Death, especially death in marine mammals, you have to look at the brain. Again, I'll talk about that in a second. But we have seen a correlation between high levels of DDT and on San Miguel Island, increased spontaneous abortion. So in other words, the adult moms are giving birth, and the babies are born, but they're stillborn. So, and when they looked at, why was this happening? The only thing they could find was very high levels of DDT in the tissues of the mom. So that's a correlative effect. And also an increase in reproductive cancers along the reproductive tract in both females and also in male sea lions. All right, so getting back to humans for a second. So we have this thing called maternal offloading, which you may or may not have heard about. And maternal offloading is where an adult female, wildlife or human, will have certain levels of these contaminants in their body. And because they're lipophilic, fat-loving, what happens is the adult female will accumulate them over her lifetime. And then when she is pregnant, these lipophilic contaminants can move across the placenta and go to the baby, the offspring. And then when she gives birth and she nurses that offspring, because they're lipophilic and the breast milk is very fatty, she's then offloading these contaminants to her young. And that's called maternal offloading. We've seen this in many different mammals, and now we're seeing it in certain species of sharks and things like that. So this is a figure where they were showing the maternal offloading. This is from Veracruz, Mexico. And what you see is that the first child gets the majority of the contaminant load because the adult mom is building up these levels of contaminants throughout her lifetime. And then the first child gets the most of it. And then between the first and second child, maybe it's 2 years, the second child doesn't get as much, and then the third child doesn't get as much, and the fourth child doesn't get as much. So if you're the firstborn, you're already being loaded with these contaminants that can cause cancer and developmental abnormalities and things like that. So it's not that we're feeding our children these contaminants in our food, it's that the mom naturally is actually giving the contaminants to their offspring. Okay, let's see. So that's in humans. We see it in animals. We also see it in fish. There are very high levels of DDT. Oh, sorry, that's a different slide. Sorry about that. Okay, so we know that DDT is very highly mobile. It's a very light molecule that floats in the air. It also goes in streams and rivers and down into the ocean. It takes it up to 15 years for DDT to biodegrade. What scared scientists was when they started studying marine mammals in these very remote locations and found relatively significant levels of DDT and PCBs in these animals that were never anywhere near where these contaminants were produced or manufactured. Okay, we do know that one of the largest hotspots in the world is actually off Palos Verdes Peninsula. That's a map of the hotspot. And Montrose dumped about 1,800 tons of DDT off our coast between the 1940s to the 1970s. 110 tons still remain. You may have heard that they've tried to mitigate this. They've dumped sand over the sediment where they found the DDTs, but we have a lot of currents in our Southern California area, and so the sand just kind of gets pushed away, and the organisms that are low on the food chain will still absorb these contaminants. And again, they're lipophilic, so anytime you have a lipophilic contaminant, it's getting in the low levels of the food chain, and then it gets bioaccumulated up the food chain, and that's how it ends up in such high level carnivores. Let's see, in 1968, they found that Americans were eating up to 0.025 micrograms of DDT per day, and that's just naturally in our diet. All right, now, most recently, I'm sure you heard in the news, this was last spring, even though they actually found this new dumping ground early in between 2000 and 2013, I think it was, they recently did another expedition and got pictures of these barrels of DDT that are closer to Catalina Island. And this is where the new location is. So this is about 8 miles off Catalina Island. They mapped over 27,000 barrels of DDT degrading, the barrels are rusting out off Catalina. And they think there may be up to 100,000 barrels of DDT sitting out there. And really, it's been there for years and years and years, and there really is no way to clean it up. Now, remember that this is getting, bioaccumulated into organisms that we eat. And so one example is white croaker off our coast right here. All white croaker have very high levels of DDT in their tissues. And in fact, if you go to any of the piers, you'll see a list of species you're not supposed to eat. Typically, white croaker is on there, and a lot of times the picture is crossed off, or scratched out, and the sign is scratched out. And I've been on piers several times where I'm walking down and I see, families fishing for their dinner, and they have white croaker in their buckets. And so they are ingesting very high levels of DDT. All right. So they also looked at DDT and their metabolites in various countries to see, who was actually getting these high levels of DDT and DDE. Now, one thing I didn't tell you previous is that when you see high levels of DDT, what that means is that the human or the animal is living very close to the point source, so where it's actually being produced, because very, very relatively rapidly, the body metabolizes it, and you would not see DDT in the body, you would see DDE. Okay, so that's significant because what you're seeing here is that DDE is higher in all of these countries where it should be, because they're not producing it, except for in Russia. Russia supposedly is not producing DDT. That's what they tell us. But we know that that's not true, because if they weren't producing it, the levels of DDE would be higher than the levels of DDT in human tissue. And look how high the levels are. So they're really getting a lot of DDT. The highest levels in all marine mammals that have ever been found have been over 2,000 parts per million. This scale right here only goes to 500. So you can imagine how high that is. However, in general, realistically, most of the levels have been 100 parts per million or lower, so somewhere around this range. All right, PCBs. Let's talk about polychlorinated biphenyls. So PCBs were discovered in 1865. They were started to be synthesized in 1881. And these are not a pesticide. By 1914, they had already been seen in bird feathers. These are actually this is a chemical or a contaminant that's made to allow you to, again, have something that's high in heat, but that it doesn't burst into flames. So these are going to be things that are found in electric transformers, in paints, in plastics, and things like that, not in clothing, but things like that, because they have a very high heat capacity. So these are not pesticides at all, but they're very similar to DDT, the pesticide, in how they act in the body. So by 1914, they already saw it in bird feathers. It was first manufactured in Alabama in 1927. And the industrial applications that they're used in, again, fluid and transformers, heat capacitors, inks, additives, lubricants, they're actually used or were used in carbonless paper, like the credit card receipts and things like that. All right, so there's a problem with PCBs, and that is that they actually don't ever biodegrade. So the total amount produced was 1.5 million metric tons. Again, they do not ever biodegrade, so whatever has been produced is still in the environment, and they are lipophilic, so they bioaccumulate up the food chain. They also biomagnify, so that's across different trophic levels. And they have been found in all top-level carnivores studied, everyone, including humans. They were banned in the United States in 1979, but they are still contained in everything that they were produced in that are slowly leaching out into the environment. So they're in refrigerators, they're in all of those things that, we put in landfills or that we dump in different areas, and they're leaching out into the environment. Okay, so hundreds of tons were dumped off Palos Verdes Peninsula, and as far as we know, about 11 tons remain there. All right, detrimental effects of PCBs. They are highly toxic. They cause cancer and birth defects. They are immunotoxic, so they affect the immune system. Reproductive consequences, such as decreased birth rates and decreased number of offspring produced. They decrease sperm counts. They decrease live birth rates, so more spontaneous abortions. They increase premature births. And they also have neurotoxic effects, like they decrease visual recognition in developing young, which is very important for wildlife. If they can't recognize their mother or other organisms like that, it's very, very difficult. They won't survive. It also decreases the short-term memory and decreases the ability to learn. Now, along with DDTs, PCBs also cause feminization of male organisms, because both DDT and PCBs mimic environmental estrogens. So they mimic female hormones. And when they do that, they're taking the place of a hormone in females, but also they're making a male organism have too many, you know, synthetic female hormones, and male organisms like fish are developing female attributes, which means that they can't reproduce. So that makes the population of these organisms decline because the reproduction is affected. So that's also scary. All right, this is a figure that shows you the PCBs in the blood of Arctic residents in different areas, and you can see that it's actually pretty high. Now, this is significant because when they showed these maps to indigenous peoples in the Arctic, they stopped actually eating traditional foods like fish, where the PCBs were highest, and they started eating, I'm not kidding you, things like McDonald's and fast food, which also is really bad for you. So they swapped one bad health thing for another bad health thing. So non-traditional, non-healthy foods. All right. I also always like to throw this in here because, you know, if you are, you know, interested in farm salmon, I know a lot of people that say, oh, I only eat farm salmon. And, you know, farm salmon actually is not very good for you for a number of reasons. One being that they're feeding the salmon itself, they're feeding it concentrated pellets, which they wouldn't normally get in the wild. And so farm salmon actually has a much higher fat level than wild caught salmon. And so if you're eating it to be healthy, you're actually getting a lot more fat in your diet. However, the other problem is that you're getting a lot higher levels of these lipophilic contaminants. So this is an example of PCBs, and you can see beef, pork, farm catfish, poultry, milk, typical commercial seafood, and then look at the farm salmon. Look how high that is compared to wild Alaskan and Canadian salmon. So you really have to think about the health effects of eating these farmed fish because they're really not that good for you. And you can see this other one, farmed catfish, the same problem. All right, so here's another. Can you hear me?
Yeah.
Yeah, awesome. Okay, I think I just hit the microphone. Sorry about that. All right, so let's go back to the slides. So these are PCBs in other foods, and anything that's fatty is going to have really high levels of PCBs in it. And you might notice that, so butter, tuna, those are really high. You might notice that chicken breast, roasted chicken breast, which we think of as being healthy, lower fat and stuff, it actually has much higher levels of PCBs than, say, where is it down here, fried chicken. And so people always ask me about that. And the reason is because you can actually degrade or break down PCBs with high heat. And fried chicken is cooked at a much higher temperature than roasted chicken is. So yes, it might be lower in fat, but it's actually higher in PCBs. So I always tell my students, you know, when I look at this graph, okay, that's it. I'm going on the caramel candy diet because it's really low on PCBs. Okay, so now let's talk about marine mammals because that's why you're here. Why are contaminants, why are they such an issue where marine mammals are concerned? We have, I mean, they're not ingesting it like we are, we don't think. So what's going on with this? Okay, well, for one thing, they are considered to be top-level carnivores. And I told you about bioaccumulation and biomagnification. So anything that's the highest on the food chain is going to be accumulating these lipophilic contaminants throughout their lives, okay? So they're top-level carnivores. The other problem with marine mammals is that they have very thick blubber layers, right? They're living in the water 100% of the time. And so, you know, they have to stay warm, thermoregulation. So they have really thick blubber layers. That's fat. So you're getting a high concentration of those contaminants in their blubber layers. And the other problem with marine mammals in the Southern California Bight is that they are living close to where we produced and dumped these things, especially DDT and PCBs. So they're really exposed to these contaminants.
So, all right. Marine mammals like pinnipeds and mysticetes, the baleen whales, can actually metabolize their blubber during their fasting time. So they fast for pinnipeds. Some of them fast twice a year. Some only fast once a year, mysticetes once a year. So when they're fasting, they actually are metabolizing their blubber, which means that they can actually excrete a lot of these contaminants. But for things like the toothed whales and dolphins, they are not fasting. And so the contaminants are going to accumulate for them throughout their life. All right. So what did we see what patterns of organochlorine compounds do we see in marine mammals worldwide. So let's talk about regional, ecological, and temporal variations. So the first thing that you're going to have to, keep in your memory is that in general, as I said before, you are going to find higher levels of PCBs than DDT in marine mammal tissue. And again, that's because there are relatively few places that produce DDT. And so you're not really going to see high levels unless the human or the animal was very close to that. You should, in general, see higher levels of PCBs. And that's because those species are going to be located closer to the point source. They'll have higher levels. So, and if they're closer to the point source for PCBs or DDT, they're also going to have higher levels. So if they're coastal species or they live near these manufacturing areas, they're going to have higher levels as well. Species that feed higher in the trophic level are going to have higher levels of both of these contaminants. And also, any animal or human that lives in the northern hemisphere tends to have greater levels than animals in the southern hemisphere because it was produced more in the northern hemisphere than the southern hemisphere. Now, interestingly, you would think, well, polar species, there's not much going on there, so they shouldn't have very high levels. But what they found is that polar species actually have higher levels of these organochlorine contaminants than equatorial species, and that's actually because of the transport of water from the equator to the poles. So it's actually going up to the poles and then kind of getting dumped there. And so polar species have higher levels than equatorial species. However, there is one exception, and that is polar bears. So polar bears themselves actually have lower levels than other marine mammals. And that's because they have the unique ability to metabolize certain organochlorine compounds. And so they don't store them. And they also don't have as thick of a blubber layer. All right. So what about age, sex, and reproductive status? Well, I talked about the maternal offloading, and so that leads us to this. When you're talking about juveniles, there's no difference in sex. So juvenile males and juvenile females have equal concentration levels in their bodies. We do see that these concentrations increase with age in males, also in females, but then once the female gets to be reproductive age, she will dump the contaminants to her offspring. And so it decreases with age once they're in their post-reproductive status. As an example, they did a study and they looked at gray seals, and they found that the moms actually transfer 98% of their organochlorine load to their offspring, 98%. So that means that in the adult female, they're going to drop really greatly, but in the offspring, they're already starting out, both males and females, with very high levels in their tissues. Okay, and then what are some of the impacts on marine mammals? Well, as I was saying before, it's actually really difficult to show cause and effect for any kind of contaminant on a marine mammal. And that's because when they are doing, a necropsy on a marine mammal, what they're looking at is the brain. So the diagnostic cause of death is they're looking at the brain, and the brain, because it has phospholipids, not the other kind of lipids, the contaminants actually don't concentrate in the brain. So you have to really do a correlation study where you look at the contaminants in the tissue, then see that it died, and then say, okay, we ruled out parasites and everything else. The only thing we can think of are contaminants. So super hard to say 100% without a doubt that it's contaminants, but we do see these correlations. Okay, so we already talked about, so no evidence for like direct mortality, like, we can see with lung cancer and cigarettes, something like that. We can't really see that. But we do know, we have seen the increased reproductive impairment, susceptibility to disease. So they did correlations between phocine distemper virus and these organochlorine contaminants, and saw that when there was that big phocine distemper virus die-off of seals in England, Ireland, and Scotland in the 1990s, there were also very high levels of organochlorine contaminants in their bodies. And also more recently, they're trying to see if high levels of these contaminants also lend itself to more animals dying when they get domoic acid. So is there a correlation there? So possible link there. All right, so that's kind of a worldwide picture. That's the background on the contaminants. That's the worldwide picture. What about what's going on in Southern California? So I had a graduate student that did a study on Southern California pinnipeds. And she looked at 3 different pinnipeds and collected samples from the marine mammal stranding centers in Southern California. So we did, she looked at the 3 most common pinnipeds that strand in Southern California. So there was the Pacific harbor seal. Pacific harbor seal, as you probably know, lives and feeds year-round in the Southern California bight. They are opportunistic feeders on fish and squid, but their main prey are things like plain fin midshipmen, Pacific whiting, octopus, market squid, and a variety of rockfish and some flatfishes. But so they're considered to be kind of generalist feeders, but they do focus on a few species. Actually, pretty wide variety of species. We also have the California sea lion, Xylophus californianus, and for them, the females live year-round in the Southern California bight, but the males and the juveniles go north to feed in the winter. They are also considered to be opportunistic or generalist feeders on fish and squid. They mainly like northern anchovy, Pacific sardine, Pacific whiting, and loligo market squid. And then we have the northern elephant seal, which does not spend much time down here. They mainly use the Southern California bight for some breeding and molting. All of them feed and pretty far offshore and in the northern waters. They have the least varied diet. Mainly they're feeding on squid, which are pretty low, not fatty, not very fatty. So the squid themselves would have lower levels of contaminants. But they do feed on some fish and a few elasmobranchs, mainly towards the bottom. But they're going to feed on organisms that are the lowest of the 3 pinnipeds. Okay, so the study area was the Southern California bight, and again, we collected samples. Actually, the Marine Mammal Stranding Centers actually collected samples for us and stored them because they thought they were going to do something for us. Right before we started the study, the Pacific Marine Mammal Care Center actually threw out most of their samples, so we didn't get a large number from them. But we got the most from MMCC, so we got 125 samples from them, and from the Pacific Marine Mammal Center, we got 20. And they had been collecting those samples since about 1994, so it was really good because we could see how the contaminants in the tissues changed over time. Okay, so let's start with this graph. So what we see is on the, excuse me, I have a frog in my throat now. On the x-axis, we have PCBs, total PCBs, and on the, and we also have total DDTs. We have different colored bars or shaded bars depending on what animal we're talking about. So the black is the Pacific harbor seal, the light gray is the California sea lion, and the dark gray is the northern elephant seal. And this is a log scale. So this is showing you the log of the contaminant by the lipid weight. So normalized to the amount of lipid that was in the tissue. All right. So the first thing that we see, excuse me, is that the levels of PCBs are much lower than the levels of DDT. And in fact, that was significant. And that makes sense because, once again, we produced and dumped a lot of DDT off our coast, but we didn't really produce and dump a lot of PCBs off our coast, much more DDT. So that was really expected that we would see higher levels of DDT. However, remember, worldwide, for almost every other place, you're going to see higher levels of PCBs. So that was pretty interesting. The next thing that we saw was that if we look just at PCBs here for a second, we see that there was no difference in levels of PCBs between the harbor seal and the California sea lion, which are spending a lot of time in the Southern California bight and also feeding higher up on the food chain. But there was a significant difference between these 2 species and the northern elephant seal as far as the levels go, and northern elephant seals had significantly lower levels of PCBs. Again, they're not feeding high on the food chain and they don't spend a lot of time here. We also saw the same thing with DDT. So same thing, higher levels in Pacific harbor seal and California sea lions, no difference in levels between those 2 species, but those were both significantly higher levels than we see in the northern elephant seal. Another thing that we see from this graph is that these levels were relatively high. And in fact, what they've done studies and they found that concentrations above about 17 milligrams per kilogram of lipid weight have been linked to suppressed immune system function. And even though the concentrations of PCBs were lower than DDT, for every species that we saw, we saw a higher level, higher than that 17 milligrams per kilogram. So in Pacific harbor seals, it was 48% higher, sea lions 36% higher, and northern elephant seals 23% higher. So we know that, that causes a suppressed immune system, and that these animals actually had levels high enough to cause a suppressed immune system. For PCBs, we found that they were up to 6.4 times higher than in other pinnipeds that were studied in California. And in DDT, because we're in the Southern California bight, up to 29 times higher than any other pinnipeds that were studied in California. All right, now looking at the California sea lions just by themselves. So we wanted to look at age and sex, and the sample sizes for the other two species were relatively low. So we only had enough samples to look at California sea lions if we wanted to look over, by their age class and also by their sex. So again, we have log concentration of DDT per lipid weight on the y-axis. Here we have age class. So we have pups, yearlings, they're year-old, subadults, and adults. And again, the black bars are male and the gray bars are female. And so what we see is that it's pretty interesting. It's kind of what we already talked about. So females have a 93% lower levels of DDT than males. And we attribute that to the maternal offloading. And that's highly significant. If we compare the females to the other age classes, we see that all the age classes are pretty much the same. So there's no difference between males and females in any of the age classes. And we also see that females had an 81% lower level of contaminants of DDT than all of the young. So again, that lends itself to the theory, they are getting rid of these contaminants to their offspring. Same thing for PCBs. So this is the same graph only for PCBs. And again, we see in this case, it's 94% lower for adult females than males. And for the adult females compared to the other age classes, we see that they have 81% lower levels of total PCBs in their body, and no significant difference among the various age classes because they're similar. They're not offloading those PCBs. All right, now let's look at over time, what happened over time. So we'll start with northern elephant seals. We didn't have enough samples to do the harbor seals, so we don't really know what's happening with them over time, but we did have the northern elephant seals. So, so let's start with what's going on. So again, log concentration micrograms per lipid weight, and this samples for elephant seals we had between 1996 and 2006. PCBs are the black circles and the white are DDT. And you don't see any lines on this graph because what that means is that there was actually no change. There was no significant change over time. So it didn't go down, the levels didn't increase in tissues, the levels didn't decrease in tissues, but that actually makes sense because they're really not spending a lot of time here. And if you look at the y-axis here, their overall levels were actually relatively low. So it makes sense that you're not going to really see a change over time. If we look at California sea lions, on the other hand, we do see these lines going down, and that's because, over time, those contaminants are actually, going into these animals who are then dying. And so over time, the levels are actually decreasing in the environment and also in these animals. And so in California sea lions, we saw that they did decrease, but they're still at really high levels. So if you look at the scale here, here we're at like 2, here we're double the amount. And so their levels are still really high in these animals. Okay, then we compared what we found with other pinnipeds worldwide. So we'll start with PCBs. So with the California sea lion, let's just go over this real quickly. This is from the stellar sea lion from Alaska, negligible levels of PCBs. This was a very small study on California sea lions that were from the Central Coast. And they didn't give error bars. So this actually is the total number, and they had a very, very high variability. I'm not really sure why, but they had up to 1,300 parts per thousand. So we're not really sure why those levels were so high, but their sample size was really low. This was Northern California. So Northern California sea lion study, also okay sample size, but they had their levels were about half the concentration of what we found in our study. for Pacific harbor seal, so that's ours in the blue, Pacific harbor seals. There were no other studies done on Pacific harbor seals, so we compared it to other types of phocids, and we had gray seals, Caspian seal, and harbor seals, and then the Pacific harbor seal. And basically, the Pacific harbor seal had the highest levels of PCBs in them. So these were mainly from the Atlantic. And then in the northern elephant seal, the first group were from Año Nuevo, and this group was from Central California. And again, because they don't spend much time in the Southern California bight, we really didn't see a difference there. It wasn't higher like we saw in the other species. Same thing with the DDT, pretty much the same thing. High variability, really high levels in the sea lions, really high levels of DDT in the harbor seals, much higher than anything we had tested before, and then pretty low in northern elephant seal. But once again, they don't really spend much time in the Southern California bight. All right. And then the last thing we looked at was the mean levels of PBDEs. Remember, those are those flame retardants in California sea lions, and compared it to the Pacific harbor seal and the northern elephant seal. And basically, the sea lions had significantly higher levels than the harbor seal, and both had significantly higher levels than the elephant seal. Also, the adult females were lower than the juveniles, again, lending it to the theory of maternal offloading. All right, so the summary, DDT levels were higher than PCBs in the Southern California bight, which is the reverse trend that is seen worldwide. And that's because we have the Palos Verdes hotspot here. Total PCBs, DDT, and PBDEs were the highest in Southern California sea lions and the lowest in northern elephant seals. Again, they're spending the most time in the bight for the California sea lions. They're also higher in sea lions and harbor seals than in any other area really measured anywhere that we know of. And contaminants are highest in adult males and the lowest in adult females due to that maternal offloading. The other thing is that contaminants are still high in California sea lions in the Southern California bight, even greater than 30 or more years after dumping has ceased. And that's because it's still in the sediments, and now we still have those barrels that are, still leaching out these contaminants into the environment. So it's going to be a long time before the levels actually get down to, something that's really workable. All right, I think I am out of time, so I'm going to skip the part about the Palmyra Atoll. I will just tell you that that at Palmyra, which is a very remote area, we found very, 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 very low levels of contaminants, of these contaminants in the 3 cetacean species that we looked at. And that's a really good thing, because we know that it's not, at least we're not seeing high levels in these really remote areas. So that's all I have today. And I acknowledge the people on this slide, which helped do the research and did some funding, and it's a really, really good study. Are there any questions?
Awesome. Thank you so much, Dr. Goodmanlowe. I want to say it was fascinating for sure. Fairly depressing, I would say.
I would say so. Yes. I always teach this at the end of the semester, and I warn the students that this is the most depressing part of the semester. So yeah, I get it.
I think people are gathering their questions right now, but as they're thinking of those, we're faced with some pretty dire situations here where we have a problem, and it's difficult to mitigate that problem. Is there, other than the attempt to pour sediment over some of those areas, is there anything that's being done, or have they given up in trying to figure out how to mitigate the problem?
I don't think they've given up. I just think I personally don't know how they can do it, because you can't remove that much sediment. And then where would you put it, right? Would you put it in a landfill? So, and the ocean is moving. There's currents, there's gyres, the sediment is always moving. So you can't really bury it. I mean, you could throw a lot of money at it and bury it, but it's still going to come back up, right? So, and the same thing, like with the cleanup of those barrels they found off Catalina, what would they do with that? I mean, you can't, if you burn it, it's going to go into the atmosphere. If you haul it up and put it in on land, it's going to leach into the environment that way. So I personally don't know of a good way. So, yeah.
Assuming you can even get it off the bottom
As
without
soon as you,
disturbing it.
because the barrels are degrading. Like, how would you even do that, right? Yeah.
Well, we're not getting a ton of questions out.
All right,
I think you had a
that's
very
okay.
thorough lecture today.
It's a Friday
we have a
night.
question
Everybody
here.
wants to go home.
Probably. From Heather Turks, we have a question. There was a graph on an early slide that showed the creation of one contaminant, ring seals and milk. There was a drop in the levels for milk. Any idea what caused that drop?
Let me go back. So was it the, let's see, I think I know which one you're talking about. No, it's not one. Was it this one?
Heather, do you want to unmute yourself?
Was it this slide?
Yes, that was the one. So we see the drop there. I'm not sure what the bottom axis is there.
Okay.
Any ideas of what caused that at that time?
So this is, so the blue is the ring seal, so that's still going up. Excuse me, my cat's here. The green is the levels in human milk in Sweden, and that dropped. So I don't actually know why that dropped, other than maybe they stopped drinking milk, or I'm not sure, actually. I mean, they might have stopped. I mean, maybe they stopped breastfeeding. I'm not really sure, actually. It's a good question. But that was in human milk. Yeah.
We have another question. Are there any similar studies in whale and dolphin species, especially those that migrate through our area?
Yes, there have been a lot of those are, it's a lot harder to get those samples, and so those have not been done as often as pinnipeds. Here, I'll show you this graph. This was from the part that I didn't talk about. So the problem with getting samples with cetaceans is that you basically have to use like a bow and arrow sampler, and a lot of times it bounces off. And so and also you can't, it's very difficult to get age and sex, because you don't know if you're taking a sample from the same exact animal that, you know, the next day that swam by. And so there's a lot of limitations, but this is I did a comparison for our data versus other bottlenose dolphins and spinner dolphins that had been studied worldwide. And you can see, this shows you that, so the circled ones are the Palmyra, the remote location ones, the ones that we did, those are circled, and you can see it's really low. But look at the levels of these other bottlenose dolphins that, you know, are found in all these different areas. So yes, and the people are working on that more and more. But again, it's a lot more difficult to collect the samples and also know what age of the animal is and what the sex of the animal is. So it's more like an overall study, and the sample sizes are lower. But yes, and it's not good.
Sample sizes are generally low for cetaceans, right?
Yeah, right.
So Scott Valentine had noticed that many of the studies were done a little while ago. Are there current and ongoing studies?
I'm sure there are. I haven't seen anything really published, you know, especially in Southern California. I haven't seen anything more recently. Probably it's going to be on cetaceans, but they're always studying this, you know, everywhere, because the contaminant issue is not going away. So the study that we did was pretty long ago, and as far as I know, no one's done any pinnipeds in Southern California since then. But I know worldwide they still, you know, I still see papers that are published on this stuff. Once they kind of figured out the methods, then everybody started doing it to try to figure it out. And it's pretty bad worldwide.
Yay.
Yeah.
So, you know, the idea of you know, getting out there and actually doing something to help solve the problem is a daunting one. But how do, you know, are there things that people who are passionate and interested could be doing to make sure that this stays as an area of public concern? Is there anything that could be done to make sure that the resources are out there to make sure that we're doing all we can to help to mitigate these problems?
That's a great question. And normally I try to be upbeat. And, when I'm talking about plastic pollution and, electric cars and things like that, I can really say, yes, there's so many things we can do. But I don't think there is a lot that we can do at this point. For one thing, the United States banned these production of these chemicals a long time ago. So these are leaching out from the environment where they've already been dumped. So it's really, really hard to really, do something about that. And then the other problem is because we see so many other things in the environment, like, the Pacific garbage patch, that's like in our face all the time. And that is something that we can do. We can, try to reduce our use of, single-use plastics and things like that. And we can try to clean it up because we can see it. So in the case of these contaminants, I'm not sure that I can be positive about that because I don't really know how we can do that. I don't know how we can keep it in the forefront, of people's minds and get money to mitigate it. And I don't even know how to mitigate it, So that would take some engineers or greater minds than mine to figure that out. But so I'm not sure. I guess the answer is I'm not sure about that.
Well, that always leads to perhaps some people who are watching today to make sure that they are thinking about those things and investigating themselves.
That is true.
Oh, question about Montrose and accountability. I know that there has been funds dedicated based on the Montrose chemical plant, but do you have any information on that?
I do not. I don't know anything about that. No.
So I know very little, and there has been litigation and awards being made towards the fact that this has happened.
Right.
And those funds are still being used today for various campaigns and various support. Just recently, I think they put some rock out to develop habitat for kelp forests within the area. So that's one thing. I think one thing that we can always think about is the, ourselves, the environment, marine life. There's innumerable threats that all of us face, from climate change to chemical pollutants to plastic pollution. And one of the things that we can do if we can't solve, one problem specifically, there's certain areas that we can help to reduce or mitigate and limit the number of stressors that these animals might have and might face. Yeah. So if you don't want to have an animal that's simultaneously suffering from lack of food supply, lack of area to breed and all those things, and then layer upon other issues. So, if we can't solve all the problems, at least we can solve many of the problems and work to mitigate the issues that way.
Yeah, and I mean, you have to remember that, all these things kind of work negatively together, right? So plastic pollution leaches, environmental estrogens into the environment. So all of these things are working together against the animal, right? So if we can help get rid of some of the other stressors, as you were saying, that actually benefits them, even if we can't get rid of these contaminants 100%.
Diane Alps put a little EPA.gov link about the Montrose settlement. So awesome. Thanks, Diane. And thank you, Dr. Goodmanlowe, for taking some time out of your Friday evening to join us here. I hope everybody is staying happy and healthy. And we wish you all a wonderful, happy new year. And we'll see you at the next Beneath the Surface lecture series.
Thanks, everyone. Thanks for coming.
Hi, Gwen.
Hi, how's it going, Diane?
Good, how are you?
Good.